Welcome to a lesson with Dr. Powell. In this video, we will look at a brief introduction to RSA cryptography in one specific case of it. So the case we're going to be considering is where the public can encrypt a message. So suppose A, B, C, D, these are different people, and they can encrypt a message and send it to a place over here, S we'll call it, and over here the message can be decrypted with a private key. So this key is known only at this location, and yet everyone here can send messages securely to this one place right here in particular. So that if the message is intercepted, no one can decipher it because they don't have the private key. Okay, so let's look at how this situation will work mathematically. Okay, so we're going to be using the Euler-Phi function. Remember what this computes. This computes the size of this group right here. Z mod n z cross, so the multiplicative group mod n, it computes the size of that, and we want the size of that multiplicative group to be kept a secret. How do we keep it a secret? Well, how do we compute the Euler-Phi function? By knowing its factorization, the factorization of what we're putting into it. So if we can make the factorization really hard, or a number that's really big so we can't factor it very quickly, then we're going to be safe. So we want to keep phi of n a secret. We don't want anyone to be able to figure that out. We do want the public to know the number n though. Okay, we want them to know what mod we're working in, but we do not want them to know what phi of n is, because if they do, then they can, when they intercept the message, they can figure out what the private key is and decrypt the message when they shouldn't. So the way we're going to encrypt and decrypt is actually by exponents. We're going to use the fact that exponents in a mod actually live in a different mod. They live mod phi of n, the Euler-Phi function. Okay, so and the messages are going to live in this multiplicative group mod n. Now if we choose our n wisely enough, the probability is basically just about 0 that we're not going to be, that something's not going to be in this multiplicative group. So that's a good thing. The way we're going to encrypt is we're going to take a message, something in this mod, this multiplicative group, and we're going to raise it to the exponent of e. To decrypt it, we raise it to an exponent of d, and that'll get us back to a bar here, where the bar is referring to mod. So the bar is going to refer to mod n, and this little squiggle right here is going to refer to, so let's let bar refer to mod n, and we'll let the squiggle refer to mod phi of n. Now these exponents right here, e, d, multiply, and remember the exponents live mod phi of n. We want these exponents to multiply in that mod to one squiggle, so that it'll be like a bar to the one squiggle. The exponents behave in a mod here, so it'll be like a bar to the first, so it'll just be a, which is exactly what we want. So to find the decryption exponent, we just simply have to find the multiplicative inverse of e mod phi of n, and then we're going to be well on our way. Let's look at an example here of a situation. Suppose we chose our number n very poorly, extremely poorly here. Let's just let it be a small prime number. We know exactly how that factors very quickly, and the computation of the Euler-Phi function of it is very fast. So the Euler-Phi function of n, what is this? I mean, we're computing the size of, and we're sticking a 19 in here. We're computing the size of the multiplicative group mod 19. This is simply the number of numbers from 1 to 19 that don't share any common factors with 19? Well, we only have to exclude 1, 19 itself, because it's, prime. Everything below it doesn't share a common factor. So therefore we know that this number is simply 18. So the exponents will live mod 18, and the messages will live mod 19. Okay, so let's get started. What we want to do then is we have an encryption exponent, and we've intercepted a message. And the message we've intercepted is 6. And you can think of this as a bar if you want to, because it lives in this multiplicative group. So mod 19 is the bar here. So we've intercepted this message, and all we know is this is what the public knows. The public knows how to encrypt, and it knows n. But we also know what phi of 19 is. So using that information, we're going to find the decryption exponent. So the decryption exponent, so this is E is squiggle. The decryption exponent is going to be the inverse of 7 squiggle. So the inverse of 7 mod 18. So we run through using matrices to find the inverse of 7 mod 18. So we can write a division algorithm line. 7 times what gets us close to 18? Why don't we do 7 times 3 with a negative remainder of 3. Okay, so we're creating a remainder sequence, 18, 7, 3, and then we take the 7 and the 3, and on the next line we say 3 times 2 gets us plus a 1, gets us close to 7, okay, or gets us to 7. So we have a remainder sequence that looks like 18, 7, 3, 1. Of course, we had a negative in there, but we're going to take the positive remainder in our sequence. The negative will be reflected in how we move from 18.7 to 7.3 to 7.3 to 3.1. We're going to do this with matrices. You can look at my video on the extended Euclidean algorithm for more examples and detail on how this works. But so I'll be more brief in this video on that on this. So what we have is we start off, we're going to have two matrix functions, composition order, so first the one on the right and then on the one on the left. The first one, we look at the quotient right here. See this 3, and that's going to enable us to write down the matrix that we want, 0, 1, negative 1, 3. For a negative quotient, or for a negative remainder, that is, sorry. For a negative remainder, what we do is it's always going to be the form 0, 1, negative 1, q. For a positive remainder, it's always going to be the form 0, 1, 1, negative q. So the difference between this is this line, is this bottom row is just the negative of this one, and that's to offset to make things positive again. Okay, so and the idea is that to move from 18.7, like if I were to plug 18.7 into this matrix, what I get out is 7.3 actually, and then that comes into the next matrix function, should give me out a 3.1. Okay, so we have that this right here is going to be equal to 3.1 if I put in a 0, 1, 1, and with this quotient right here, a negative 2. Okay, all right, so matrix multiplying this out, I only want the 1 right here will help me, so I'm going to remove this row right here, and just because that'll pick out that bottom entry 1. Matrix multiplying the 1, negative 2 to this matrix right here is like thinking of this 2 by 2 matrix 0, 1, negative 1, 3 as being a row matrix function where I input a row and output a row, which is like 1 times, so this 1 right here, 1 times the top row plus -2 times the bottom row, like 0, 1, 2, -6, and then add, you get -5, 2. Okay, so we end up getting this nice computation. 2, -5, 18, 7 is going to be equal to 1. Now when we mod out by 18, so introducing squiggles, notice this part just goes away as 0 squiggle, and this computation really amounts to just -5 squiggle times 7 squiggle is equal to 1 squiggle. So we've actually found the inverse of 7 squiggle. It's -5 squiggle. Okay, so we have our decryption exponent. Uh-oh, now we can decipher the message, right? So the intercepted message was 6 bar. This is bar is mod 19. So we're going to figure out what 6 bar to the -5 is, all right? And that'll be the message, the original message from the sender. Okay, so let's work through that. So here we have 6 bar to the -5. To think about this, think of this as 6 bar to the -1 to the 5, and 6 bar to the -1 is just the inverse of 6 bar in the multiplicative group. So 6 bar to the -1 mod. So remember, this is in the base. So where does 6 bar live? It lives mod 19. It's true. 5 itself lives mod 18, but what we're computing down here below exists mod 19. So we need to find the inverse of 6 bar mod 19. So we can do that. Okay, so we get 19. Okay, so we have 19 is equal to 6 times what gets us close? Oh, well, this is pretty simple, right? So 6 times 3, right? 18, so plus 1. Okay, so our one liner with a quotient of 3 looks like 0, 1, 1, -3. And if you multiply that to 19, 6, but get rid of that row, and then you're going to get a 1, and this is actually in bars, okay, because we're working mod 19 here. So modding out by 19, actually notice this computation, so this is a 0 bar is paired with that 1 bar. We get -3 bar times 6 bar is 1 bar, which tells us that the multiplicative inverse of 6 bar mod 19 is -3 bar. So we can replace this 6 bar to the -1 with just simply -3 bar, and we want to raise that to the 5th power, and this result is interpreted mod 19. So the outcome that what we get is mod 19. So we can work through that. We can just piecemeal it. -3 squared is 9 bar, and then we can take, and then we can keep going. Let's see, and we're working mod 19. Now we could, yeah, I mean, we could think 9 bar, or we could even think 9 bar is -10 bar, if you like that better. I don't know. I mean, we could try it. So so we have -10 bar, and then we can square that. If we square that, we end up getting well, square that, we get positive 100 bar. So -3 bar to the 4th is going to just simply be 100 bar, and we're working mod 19, so we can think, okay, 20 times 5 gets us to 100, so 19 times 5 is going to be 5 less than 100, so that means this must be 5 bar. Right, okay, because it's going to be 5 more than a multiple of 19. So we get -3 to the bar to the 4th is equal to 5 bar, and then we can think, okay, and then we want -3 to the 5th, which is just going to be this 5 bar times -3 bar, right? Which is going to be -15 bar. And we're working mod 19, which means we're going to end up getting 4 bar. So the original message from the sender was 4 bar. We just decrypted it by hand using these smaller numbers, but working through the process and the ideas of how this would go. So in general, we do want our n to be very large so that this doesn't happen, so that we don't have someone coming in and saying, "Oh, I know how to find this decryption key," and then using it to actually uncover the messages. Thanks for watching.